What I'm going to do today is that I want to continue on the topic of the separation of variables. We did one example on Cartesian coordinates. We started actually last Thursday. We continued, and so that was very basic and important example. I hope you guys had a chance to review that, read the textbook on that. And then we started the second example. A lot of common things with the first example, but the geometry was a bit different. So we started that, we didn't finish. So I'm gonna recapitulate what we talked about on that example, and I'm gonna continue finishing that on Cartesian coordinates, and then I'm gonna move on to spherical coordinates. Conceptually, they are similar, but the type of the equations, and mainly because Laplacian in spherical coordinate has different shape, the ordinary differential equation that we get after separation of variables, they have different shapes and there are different type of solutions for that. Again, conceptually, they are very, very similar to each other. So I'm going to start a spherical coordinate and I will do 3 examples on that. Probably not all of them today, but there are 3 examples in relation to the spherical coordinates for separation of variables. I'm going to start them today and then see how far we can go. Okay. So the example we had was example 3.4 from the textbook. Okay. And we had a specific geometry that there was a rectangle shaped, let me write better. This rectangle shape is a cross section of a hollow that you can imagine. The cross section is on the XY plane, and it's moving from positive B to negative B. The top is A. So this is the dimensions we have. And in terms of the potential on the right-hand side surface, the potential is V naught. On the left-hand side surface, the potential is V naught again. On the bottom surface here, V is just 0. On the top surface, V is 0. And the question is, what is the potential inside this? Okay, and as I said, what we see here is a cross section, so everything extends all the way from negative Z to positive infinity on the Z axis. Okay, so that makes the whole problem independent of the Z axis. Okay, so the potential, whatever potential we want to calculate, it has to be potential of 2 variables, X and Y. So V is going to be V of X and Y, and then this idea of separation of variable is that we can write it in terms of X of X and Y of Y. 2 functions. The first one is only function of X. Second one is only function of Y. Okay. And then we said if we do separation of variable, we get ordinary second order differential equation, and solution for each of them for X has the shape of A times e to the power of kx plus B times e to the power of negative kx, and then solution for Y has the shape of C sine ky plus D cosine ky. Again, A, B, C, and D are constants. They're technically fitting parameters that we want to find them out based on the boundary conditions. And as we discussed before, some of them are easier, some of them are a little more difficult, but the idea is that these X and Y are general solutions and we need to narrow down based on the type of boundary conditions that we have. Okay, so here, a couple of very specific boundary conditions. The point is that here the geometry is very symmetric with respect to Y-axis. That means it's even with respect to X. So whatever happens at positive X, the same thing happens on the negative X in terms of the location of the boundaries, plus B, negative B, and in terms of the value of the boundary, plus B and negative B. So the function X should be an even function, okay? And in order to make it an even function, we need to choose A and B such that they are exactly the same. Okay, so this one must has the shape of, let's say, B should be equal to A, and this should be A times e to the kx plus e times to the negative kx. And this is technically a cos hyperbolic function. Let's go A cos h of kx. Okay, so this is the x component. The y component has similarities to the previous example we had. The function should be 0 at x equals 0. At y equals 0, the function must be 0. That means the second term, that is cosine of ky, must be 0. Okay, cosine of ky is 1. In order to make it 0, the only option we have is that we set d equal to 0. Okay, so the second term should vanish because of the boundary condition on the y equal to 0. Okay, and then we have sine ky. Sine ky, the good thing is that at y equal to 0, it's always 0. Okay, we don't need to worry too much about that side, but at y equals a, this needs to be 0 as well. Okay, so that means regardless of the value of c, we have certain options on k so that we can make the sine of ky become 0 at y equals to a. Okay, and that means the k values here should be like n pi divided by n divided by a. A is the length here, and n values can be anything like 1 or 2, 3, and so on. Okay, so here, by making x symmetric, by making x even, we take care of the symmetry on the x. By setting d equal to 0, we took care of the boundary condition at y equals 0. By setting k equal n pi over a, we set the boundary condition and what at y equals a. Okay, so now I can rewrite the general solution, which is now much more simplified in terms of, I would say, v of xy is, now x should be this, a times cos h kx. And then for the y, the second term just vanishes. I only have c sine k y. Okay, now if you look at this, we have two constants here. One is a, one is c. So it's okay to get rid of one of them and combine them into one constant, a c here. And then here we have sine kx. K itself can only have the shape of n pi over a. That's the only format it can have. So I would write this as n pi x over a. And then here we have sine of ky. Again, k has this shape, so I'm going to make this n pi y divided by a. And this is so far the general solution we have. Okay, so now the question is it enough? Can it be the solution with the c? The answer is no. We took care of the boundary condition on the left and right in the way that we set them symmetric. Okay, so x is even as a function of, x is even in terms of x, but now the point is that we are not still meeting the boundary conditions here. The good thing is that this function is symmetric, this function is even, so if it satisfies the boundary condition on the right, it's going to satisfy the boundary condition on the left too. Okay, so we need to just look at one of them and try to fix that, and once we are done with that, we are technically know what the solution of our problem is. Okay, so this is not yet complete. And again, if this is a solution, any linear combination of this answer with different values of n should satisfy the Laplace and the rest of the boundary condition too. Okay, so I'm going to rewrite that in the format of, let's do it here. I'm going to call that Cn because we are doing a linear series for this, and I can sum this over n. N can be from 1 all the way to infinity, and this is the v of xy, and this is the general solution so far. Okay, now if we go to this point on the right hand side boundary condition at x equal plus b, what we have is here x is b, okay, and if we look at this summation, that should be equal to v0. Okay, so let's write it down on the bottom here. V of by, all right, v of by should be a summation of n equal 1 to infinity of Cn cos h n pi b over a. Okay, so here x is a. So technically this cos hyperbolic function is now a constant. N pi b over a times sine n pi y over a. Okay, so this is boundary condition at b, and that has to be equal to v0 constant. Okay, now we need to find how we can make this happen. Okay, again, to make this happen, okay, this looks like a Fourier series. We need to come up with solutions for Cn, this constant as a function of n, in a way that this series converges to v0. Okay, so the same trick as we did before, we can multiply this side of the equation and right-hand side of the equation, which is only a constant, by sine n prime pi y over a. Okay, so we multiply it by that, and we integrate it from 0 to pi. Okay, 0 to a. And once we integrate that, because the sine functions are orthogonal, all the values on the left-hand side become 0, except for the cases that n and n prime are the same. Okay, and that way you can isolate individual Cn's from this summation, and you're going to find them as a function of an integral on the right-hand side. Okay, so let me do that. Here, I'm going to rewrite this side and multiply by sine n prime pi y. So we get the sigma here, n equals 1 all the way to infinity, Cn cos h n pi b over a. Okay, and mind that Cn and cos n pi b over a are not functions of y, so that I can keep them here, and then once I multiply by sine n pi y over a times sine n prime pi y over a, and integral, I can keep these out of integral, and I keep this inside integral from 0 to a dy. Okay, so this is the left-hand side of the equation. The right-hand side is much more simple. It's just v0. It's a constant times the integral of 0 to a sine n prime pi y over a dy. Okay, so what I wrote here on the top is exactly the term here, the same equation. What I did, I multiplied both sides by sine n prime pi y over a dy, and integrate that from 0 to a. Okay, so now if we do this, I said here all the values become 0 except for the cases that n prime is equal to n. So from this side, with this summation and integral and everything combined, we just get a term like this: Cn prime cos h n prime pi b over a is equal to this integral, which is v naught integral of 0 to a sine n prime pi y over a dy. Okay, so this integral again for the even values of n prime becomes 0, okay, but for odd values of n prime is non-zero, okay. So combine this side. I'm going to change drop n prime here because in this equation we only have n prime. So let's get rid of them and write everything as a function of n. Here we get Cn cos h n pi b over a is equal to now 0 for n values that are even, and we get 4v naught over n pi for the values that n is odd. Okay, so in a way, the part that we look at the Fourier series and the way we calculated the constant Cn's are very similar to the previous example. The only difference is that we have this cos hyperbolic function as well, but here this is technically a constant. Okay, so for values of n being even, the whole thing is 0. For odd values of n, we get this one. And now you can use this combination as a whole in this equation, which was the general solution. And if you use these values of Cn, the solution here is going to meet the boundary condition at x equals plus b and at equals negative b as well. Okay, so if you look carefully what I did, I only look at the boundary condition at plus b, not negative b. Okay, so I only look at the plus b and try to meet that one, but I had already set the x function in a way that is even with respect to x. Okay, so I'm confident if it meets the boundary condition at plus b, it's going to meet the boundary condition at negative b as well because it's symmetric. Okay, is it clear so far? Okay, so what I hope is this: you look at me doing this. Hopefully everything makes sense. Okay, but again, you are not going to learn this by looking at me. You really need to take time, read the textbook, or I'm going to upload the video, or just go over this video and try to reproduce that on your own. And do that multiple times, okay? I told you last time as well. I've worked with this many times. I taught that a couple of times. It's still before teaching, what I do is that the evening before teaching, I try to reproduce that as well, so that I can really do a step by step. See, there are multiple steps involved, and I can tell you, each step is easy, but because there are a number of steps that you need to go, it's easy to make a mistake, okay? So again, I cannot emphasize more. I really want everyone to spend time reading textbook and focus on this and to reproduce that on your own, okay? So the last step, I'm going to try to substitute the whole thing here back into this equation so that you see how the final answer will look like, everything combined. Okay, so I'm going to write that here, and that's going to be the final answer here. So technically, I'm following this, but using Cn values from this. Okay, so if Cn value is 0 or this, that means Cn should be the same thing divided by cos hyperbolic n pi b over a. Okay, or if I want to just include it here, I can get rid of this and say Cn is this one times cos h n pi b over a, and this is for n values being odd. Okay, so these are Cn values, and if you look at these 4 v naught, these two are constant. Cos h n pi b over a is not a constant, it's function of n, and the n here is not a constant as well. Okay, so for the final solution, you can write 4v over pi outside of this summation. Okay, so 4v0 over pi. This is outside summation, and what we have inside is 1 over n from the first term. So we have 1 over n here. And here we have cos h n pi x over a. Okay, guys, I need to take a minute up here. What's happening?
We don't have the book we need right now.
Oh, really?
Yeah.
Can I give you? Which book is that?
It's grammar.
Grammar?
We don't even have it. We don't have these books.
You want to use this up before the right time? That's the only option. I just forgot. I thought only. Yes, just give me a second. I'm going to give you this. Okay, I'm going to give you a piece of paper. Okay, sorry guys. I'm almost spilling my daughter again. So here in the summation, it's from n equal 1 to infinity. The one n term is this, n in the denominator, and then we have cos h, n pi x over a, and in the denominator we have cos h, n pi b over a, okay? And the rest is the sine term, which is sine n pi y over a. Okay, so this function as a whole, oh, by the way, I did one mistake. Here we only have coefficients for odd values. So n cannot be from 1 to infinity, n should be 1, 3, 5, all the way to infinity. Okay, even values of n should not be included here. Okay, that's because that's how we found the Cn values, the coefficients. Okay, so this combined is going to fit the boundary condition here, and it's going to definitely satisfy the Laplace's equation, and then that should be the solution of the problem. Sounds good? Any question? Okay, so again, the whole idea is we make an assumption that V is multiplication of two functions, each function being parameter being a function of only one single parameter. V is x of x, y of y. We came up with general solution for x and y. We tried to narrow down, okay, we tried to get rid of some of the constants here based on the boundary condition. Some boundary condition was easy, like this one, we could just say D must be 0. Some of them a little more complicated, but what we had was eventually a function like this, which is not finalized because it does not meet all the boundary condition. The boundary condition was not meeting was the one V0 at the right and left. So we started from here and we tried to meet that as well, considering that it's a Fourier series. Okay, we know it will meet if we choose the right set of coefficients. Okay, so the trick for Fourier series, as usual, is multiplying by an orthogonal function like this and integrating that. Okay, so we did that, and step by step, we could come up with a solution for Cn values, and these Cn values we put back in this solution. With those specific Cn values, it will meet the boundary condition as well. Okay, so I hope the general scheme is more or less clear for you guys.
Professor, what happened when you started writing on the left part? Like it's all equal to v naught, the integral sign, and then how does that relate to the one below it? Yeah.
So it's just right here.
Okay, and the
and
left
this
side
integral is 0 for n values for odd values of n. Sorry, it's 0 for even values of n, but non-zero for odd values of n.
Oh, okay.
Again, if you're wondering why, because if you integrate sine over odd integers of half period, it's going to be 0. So if you integrate this, it's going to be 0. If you have, if you have even values, the integral is 0. If you have odd values, you have another part that makes it non-zero. Okay, so integral over this is 0, but over this is not 0.
Got it.
That's
Thank you.
what's happening. Any more question? So if you guys have no more question on this, I'm gonna move on to the spherical coordinates, and then I'm gonna do a few examples as much as time we have. Okay. So I see my picture is a little too bright. Is that correct?
It's been like coming in and out the quality. Like sometimes it's really blurry and sometimes it's like clear. So
yeah. Okay.
But it's probably
you guys let me know. The camera and monitor are kind of far from me. If the quality is not that good or if it's too bright, just let me know.
No, I think it's just your Wi-Fi because usually it's perfect.
Okay, good.
Yeah.
All right, so now we're gonna look at spherical coordinates. Okay, so what I want to do here, I want to look at the Laplace's equation in the spherical coordinates. And then I want to look at only cases that we have azimuthal symmetry so that we don't have any dependence on phi. Okay, so that's sort of a spherical symmetry. And then I want to look at the solutions that are only functions of the radial components and functions that are, solutions that are function of radial component times the polar component theta. Okay, so R and theta are the variables we're gonna look at. So, and then I'm gonna put this back in the spherical coordinate Laplacian that has a different form, okay? And then I'm gonna look at the ordinary equations that comes out of that. Okay, so let's just start writing the Laplacian in spherical coordinates. Okay, this is technically not something that you can remember, but you should remember where you can go and find it. On most electromagnetic books, it's right the first page. On your textbook, it's right on the cover page. So if you just flip the cover page, it's on the back of that. And the Laplacian, the R term is 1 over R squared partial derivative with respect to R times R2 partial derivative of V respect to R. Okay, so this is the R component. We have 1 over R squared sine theta P over D theta of sine theta P theta. And the last term is 1 over R squared sine 2 theta. Oh, it should be sine theta. Times second derivative of V with respect to phi square, and that is equal to 0. Okay, so this is technically Laplacian of V equals 0, but in spherical coordinates. Okay, so it looks really, really nasty. Every single term has so many components. Okay, so first of all, we are just looking at the solutions that have azimuthal symmetry. So the last term here, okay, is just 0 because there is no dependency on phi. So we have these two terms. Okay, so what I'm looking at is that the solutions V as a function of R and theta being multiplication of two functions. Capital R is a function that is only function of R, and then capital theta is a function that is only function of theta. Okay, so this symbol is capital theta. Okay, it's more like an O, and then you write one H inside that, pretty much like that. Okay, so I'm looking at these sort of solutions. If we sub this back into the top equation, of course, only the first two terms and ignoring the last term, which is 0, we're gonna get equations like this. So we get 1 over R d over dr. The partial derivatives change to regular derivatives because here R is only function of R, one single variable. Okay, so you don't really need to use the partial notation. D over dr times R2 dr over dr plus 1 over sine theta one over function theta times sine theta d over d theta sine theta d theta d theta equal to 0. Looks good? Okay. Looks kind of complicated, but the same concept here. If you look at this term is only function of R. If you look at the second term, this is only function of theta. Okay, so we can separate these two. Each of these term is equal to a constant with the condition that if you add up the constant, that they has to be 0. Okay, so here, the way we choose the constants is that I'm going to set this equal to L times L plus 1, and I'm going to set this equal to the negative of L times L plus 1. Okay, so now you may ask question why I choose a constant in this format and not choosing something like L. You will see later on if we choose this format, the solutions of these differential equations are such that we can more conveniently and easily write the solution in terms of the variable just L. Okay, so for now, just imagine this is a fancy way of writing a constant. Okay, L times L plus 1. Any number, any constant, you can just write it in this format. This is L times L plus 1 for this one, negative L times L plus 1 for the second term. If you add up them, obviously you get 0. Okay, so that way we are separating the equations. Okay, you know what? I rather separate them here first and then write the second one. So I'm going to write the second equation right here. So 1 over theta. Just give me 1 minute, please. What's going on?
You said if it's just one word, you see.
Okay.
And I got this guy, but this guy got mixed up with the blue.
Okay.
So I need it to be a nice pinky color.
We don't have anything else.
As long as I won't tell you anymore. You can take this off.
Sorry, guys. So I'm going to write this equation 1 over theta sine theta d over d theta times sine theta d theta over top. So I'm going to say this is equal to negative L times L plus 1, and this one equal to L times L plus 1. So these are basically the two differential equations that we have. Okay, so these are both, if you look at them, ordinary second order differential equations. Okay, so the solutions of these are not as simple as the ones that we had in Cartesian coordinates, but again, these are more or less known equations, okay, and the general solutions are known, and that's actually enough for us. The general solution for this one is R equals, so R of R equals A times R to the power of L plus B over R to the power of L plus 1. Okay, so this is the general solution for this equation, and the general solution for this one is actually a little more complicated, but there is a function, Legendre polynomials. Okay, the solution of this equation is theta of theta is a Legendre polynomials of order L in the variable of cos theta. Okay, so for this one, we have normal polynomial, of course, with these terms of B over L plus 1. For this one, theta, function of theta, is the Legendre polynomial of order L times, not times, in the variable of cosine theta. Okay, so Legendre polynomials, I'm going to write a few of those. Actually, I'm bringing your textbook. I don't remember the first terms. Okay, so Legendre polynomials, they look like this. The zero order Legendre polynomial of x is just a constant, it's 1. The first order Legendre polynomial of x is just x. So the first few terms are easy. The second order P of x is 3x2 minus 1 divided by 2. The third order is 5x3 minus 3x divided by 2. Okay, so they have this very special format and shape. Okay, the first term is easy, just 1 second. The zero term is just 1, the first term is x. And polynomial, Legendre polynomial of order L actually has, so a polynomial with the maximum value of the same order as the polynomial order. So P3 has 5x3 and 3x. Okay, so at the end, if you look at each of them, they are not that complicated. They are just polynomial functions. Okay, but these are very useful, and there is also an equation that you can use to write the polynomial function of order L, whatever order you want, and that is PL of x is 1 over 2 to the L times L prime times L factorial d over dx to the power of L times x to minus 1 to the power of L. Okay, so this is basically what polynomial functions, Legendre polynomials are. Okay, and this is the general format of how you can find what Legendre polynomial function of order L looks like. Okay, so don't be too afraid of the weird name and French name and this weird shape. If you really calculate each of these terms at the end, they are not that complicated. They are just polynomial functions. Okay, but it's a nice thing that this complicated looking differential equation has a relatively simple solution in the terms of the Legendre polynomials. Okay, so again, going back to very first starting point, we have this spherical coordinate Laplacian. Okay, if we separate the variables, we can come up with two ordinary differential equations, and now we have the solutions, the general solution for R component and theta component. Okay, and then you will see for a lot of cases that we have a spherical symmetry and very specific dependence of the functions, charge distribution, or the potentials, the way they depend on theta. Eventually we can very nicely and easily come up with an answer for the potential. Okay, so all these complicated terms that you see on this board, eventually you see that we can very nicely and easily calculate potential by only focusing at these general solutions and simplifying this general solution based on the boundary conditions we have. Okay, so don't be afraid of the complexity here. Eventually we're going to have something very nice and beautiful for spherical symmetric solutions. So far so good? Any question? No? Okay, so what I did so far, I laid down the basics and fundamentals of separating variables for a spherical coordinate, and we came up with this general solution. And now I'm going to start one example. Eventually I'm going to do 3 examples that we use these general solutions to calculate potential. And then as we work with them, we're going to see how we can use this. Okay.
Professor?
Yes.
You know how in the beginning we had, well, from the equation we wrote down for the Laplace, there's the 2 parts, and one is, and then we, like, the arrow goes to RR and the big theta.
Okay.
So
this is for R, this is for theta.
yeah, so does the P of L, the general equation, that's only for the second
P of L in the variable of cosine theta is the general solution for theta.
Okay.
And this
whereas the P
for R.
Okay.
You know what, out of this board and the whole calculation, the only 2 parts you really need to focus is this part and this part. Okay, so these are the 2 parts that we're going to eventually use.
Okay.
Okay, and these 2 are not that complicated, so that I'm just giving you some good news. Despite all these calculations, these 2 are not that complicated. So
also, it's only in the theta one that we use the PL of X, right?
only for theta we use PL.
Okay, cool.
For R, it has very simple form, A times R to the power of L, B over R to the power of L plus 1.
Gotcha. Thank you.
Pretty simple function. Okay, any more question? No? Okay, so let's move on. So the first example I want to do is example 3.6 from the textbook. Okay, so let me get rid of everything here except these 2 equations in red box. teaching, okay? Don't disrupt. Good. Okay, so. So example 3.6 says, let's imagine you have a sphere and the potential on the sphere is given as a function of theta. Okay, so V on the sphere is V of theta. It's specified on the surface of the potential. And the question is, what is the potential inside the sphere? Okay, so we have the value on the boundary, on the surface of the sphere. The question is, what is the potential inside? Okay, so here, the idea is that we want to use the general solution and then we want to match the boundary condition. So what is the general solution for R and R? So we said V as a function of R and theta is R times theta of theta. Okay, so here we have different L values, okay, including on the top and on the bottom as well. So the way you can construct the general solution is that you can write it in terms of the summation over L, because any value of L is technically can be used. So from L from 0 to infinity, okay, and here the function R gives us two terms, A times R to the power of L plus B times R to the power of L plus 1. Okay, we can have different values for A and B depending on what value of L we have. So I'm going to use A sub L, B sub L. Okay, so this is the R component. And then we have theta component, which is the Legendre polynomial of order L in the variable of cosine theta. Okay, so this is basically the very general solution that we can have. It includes all the values of L in this form for R and for theta as well. Okay, so with that, I'm going to erase these ones as well. And this is going to be our very starting point to find the potential here. Okay, so now if you look at the shape of this, there's something very special. The R function has two terms. One of them is in terms of R to the power of L, and the other one is R to the power of L plus 1, okay? For the second term, R is in the denominator. So if you are dealing with the geometries that R equals 0, the center of the coordinate is included, the second term is gonna blow up when R becomes 0, okay? And we are certain that that should not happen because we have a specified potential on the surface, and potential is not supposed to go to infinity right in the middle of this sphere. Okay, so just by the virtue of the geometry and the fact that the second term blows up, I'm going to say this term should vanish, meaning that all the B values, all the BL values must be 0. Okay, and that's always happening when you are including the center of the spherical coordinate R equals 0 as well. Okay, so with that one, we have eliminated the second term and it becomes easier because now our general solution only has AL times R to the power of L. Okay, so it became easier because we are including the center of the coordinate. Okay, now we need to use this such that we can meet the boundary condition here as well. What that means is that if R equals the capital R, let's say the radius here, then we know that V should be V theta. Okay, so I'm going to say V of R and theta This is the boundary on the surface. Okay, so this is the potential on the surface. This, based on the solution we have, is sigma L from 0 to infinity AL R to the power of L. This is the radius of the sphere times PL cos theta. Okay, so this should be equal to a theta, the potential that is specified on the boundary. Okay, so now how is it possible? If you look at this, this R being constant, this almost has the shape of the Fourier transformation we had. Okay, so we had Fourier transform in terms of sine and cosine. This is not technically the Fourier transform, this is in terms of the Legendre polynomials, but the nice thing is that the Legendre polynomials have the same characteristic of sine and cosine in the sense that they are orthogonal to each other. Okay, so if you want to really find the values of AL in a way that this series meets the boundary condition with theta, we can multiply this by another Legendre polynomial of a different order, let's say PL prime. You multiply both sides on that and you can integrate that, okay? And that way you can eliminate this sum and only keep one term, and that allows you to write AL as a function of other variables and summation. So what I mean here is mathematically is this. Legendre polynomials has this characteristic that if you have PLX, if you multiply that by PL prime X, and you integrate that from 0 to 1, okay? Let me check something. I want to make sure it's 0 to 1. Sorry, from -1 to 1. From -1 to +1, okay? If you do that, okay, this becomes 0. Okay, meaning that if you have, just 1 minute, please. What's going on?
There's a learn. We need learn book, and you brought the wrong learn book.
I brought the wrong one.
It's the other learn book. The learn book with the two. I don't have any more learn books.
Okay, sorry guys. So this becomes PL times PL prime dx is 0. If we integrate it from -1 to 1, and that means if we use PL of cosine theta times PL prime of cosine theta sine theta d theta. Okay, so this is the change of variable. I change x to cosine, and dx becomes sine theta d theta from 0 to pi, which covers the limit of -1 to 1 for x. If we do this, it's going to be 0. Okay, unless L and L prime are the same. Okay, so this is always 0, but if L equals L prime, okay, the integral becomes 2 over L plus 1. So let me write it this way. So I'm going to say always 0 if L not equal to L prime, and 2 times 2L plus 1 if L equals L prime. Okay, so in mathematics world, that means that PL and PL prime are orthogonal to each other. Okay, if we have two Legendre polynomials of different order, they are orthogonal to each other. If you integrate that, that becomes 0. If L and L prime are the same, then they are not orthogonal, they are the same function, and you get some positive values. Okay, so this is important and useful. Okay, and that is because we can use this fact and simplify this side of the equation to isolate AL values. And those are the real coefficients that we want to use to calculate AL values in a way that we can meet the boundary condition. Okay, and so if I do that,
Professor,
yes.
For the when L is equal to L prime, what is it?
It's
Say
2 over 2L plus 1.
Okay, got it. Thank you.
Okay. So that's what I want to do here. So what I want to do is that I'm going to multiply left and right hand side by this part. Okay, by PL prime cos theta sine theta. And then I'm going to integrate that, and that's going to let me get rid of this summation. Okay, so let's do it here. Sigma L equals 1 to infinity AL RL times PL cos theta PL prime cos theta sine theta d theta, okay, and that is equal to V theta I'm trying hard to squeeze everything in one line. V theta times PL prime cos theta sine theta d theta, okay? And I'm going to integrate that from 0 to pi. The integral is over d theta, and I'm going to do the same here from 0 to pi. The integral is over d theta, so I continue to the second line. So what we get here is this integral, as I said here, is always 0 except when L equals L prime, and that's going to give me 2 over 2L plus 1. So if I do this summation over L values, all of them are 0 except when L is equal to L prime. That means I get A L prime R to the power of L prime. And here it's going to give me 2 times 2L prime plus 1. Okay. And on the right hand side, we have this equation of V theta PL prime cos theta sine theta d theta. Okay, the integral goes from 0 to pi. Okay, now if you look at this, we only have L prime, so I can get rid of the prime sign to make things looking a little simple. AL can be calculated based on the rest. Okay, so basically I can move R to the L and the second term to the right hand side and say AL is 1 over R to the L times 2L plus 1 over 2 times this integral. Okay, so that means if we know the value of R and we know the functional form of V theta, we can do this integral, and for any values of L from 0 all the way to infinity, we can calculate AL. So technically this is enough for us. If we sub it back into this equation, we can meet any boundary condition in the form of V theta. Okay, of course this is now in very general form. Okay, we don't have any specific on this, we cannot go further, but these equations are enough for us to really calculate the coefficients in a way that we can meet the boundary condition. Okay, so what happens a lot of time is that the functional form of V theta is such that we can just guess what values we need to have for PLs and how many of PL we include and what type of AL we have. Okay, so one special case, one example is that if V theta has very special dependence in terms of the sine and cosine of theta. Okay, so I'm going to continue that with a special case, and we're going to guess what type of values of AL we have. Okay, so let me get rid of this. Okay, so let's make this assumption that V theta has the form of K sine to the power of 2 theta by 2, okay, and which is equal to K by 2 times 1 minus cosine theta. Okay, so now if you look at this, the boundary condition has a form of 1 minus cosine theta. And if you remember the PL functions as a function of cosine theta, the first few terms were easy. Okay, so let's write that down. P0 of cos theta is just 1. P1 of cos theta is just cos theta. Okay, and P2, you know what, don't even worry about P2, we don't even need that. Okay, so the first few terms of the Legendre polynomials of cos theta are not complicated at all, are just simple functions like this. Okay, now if you look at this, the general solution is like this: AL r to the power of L PL cosine theta. Okay, and let's look at that summation. How does it look like? We have L starting from 0 to infinity. We have AL r to the power of L times PL cosine theta, which is the potential on the surface, and that has to be equal to K2 times 1 minus cosine theta. Okay, now if you look at this, the first term here is the Legendre polynomial of order 0. The second term is Legendre polynomial of order 1, right? Of course, in terms of cosine theta. And now, if you look at this, we are adding all these Legendre polynomials from 0 all the way to infinity, okay? By just looking at this side, we see that on the right-hand side, we have two terms. One of them is the first zeros order. The second one is the first order. That clearly tell us that we don't need to have all these summation over infinity. We just have number 0 and number 1, okay? Meaning that we can write it in terms of A0, r to the power of 0, PL of cosine theta, right? The zeros order is just 1 times 1 plus the order number 1 is A1 r to the power of 1 times cosine theta. And that is equal to K by 2 minus K by 2 cosine theta. Okay, now again, the goal was finding the A values, finding the AL values. And now look at this equation. We have one term plus another term, cosine theta, one term, another term, cosine theta. So obviously, we can just connect these and say this one, which is A0, should be equal to this. This one, which is A1 times R, should be equal to this. Okay, so these are connected and equal to each other. So here, for this specific sort of potential, we can just look at the type of equation we have and expand it a little bit and write it in terms of the actual functions and a few terms from this summation of the polynomial functions. Again, the 0 and first and second order of the Legendre polynomial function, they are not any complicated function. They are just 0, first, and second order polynomials, okay? So they look very simple. And this way we can just say, okay, A0 should be K by 2, and then A1 here should be negative K by 2. technically k by 2r because a1 times r is k by 2. Okay, and once you have these a values, of course, we know that the rest of the a's must be 0, and in this function, you have the potential inside, okay, if you use any other values of r here, and you are meeting the potential on the surface as well. Sounds good? So the shape of the surface boundary condition is going to be very illuminating on what type of the, what order and what ALs for the Legendre polynomials we can find, okay, just by matching the functions. Sounds good? Any question? No?
So, yeah, I have a question just to make sure that I'm following what's going on. So the special case is now we have a function that's dependent on theta?
Yes. The special case is that the v theta now is specified as a function of theta, and that can be expanded in terms of the cosine function. And this cosine function, 1 minus cosine theta, kind of matches, okay, kind of matches what we, matches the terms that we get from this summation in terms of the Legendre polynomials of cosine theta variable.
So it would just be following the previous steps?
I mean, yes, following the previous steps, but in the way that we just look at the first few terms and see how we can match ALs with the terms that we have in terms of the cosine. So what I have here is that I just expanded this and wrote the first term, the 0 term, and the first term. And I ignored the rest of the terms because I knew that they are not going to be useful. And I expanded this and compared this what I have on the right-hand side, which is a potential on the surface. And just by comparing the coefficients of cosine theta and another term, I could say, okay, A0 must be k by 2, and A1 must be negative k by 2 over r. Okay, and if you do this, you are already finding the solution by setting up the correct A0 and correct A1 and assuming the rest of A's are 0. It's just enough to do this, just by looking at the shape of the equations and their dependency on cosine theta. Sounds good?
Yes, yes.
Okay, good. Okay, again, I want you guys really think about this, go over the steps, think about this, and you can come back with questions. All right, so time's almost up. I'm gonna stop here. There are a couple of more examples that I will be doing on Tuesday next week, okay? Again, a reminder, the midterm is on November 19th. During the class, it's gonna be 2-3 questions. I give you, you solve them and send the solution back to me. The midterm includes all the separation of variables up to spherical coordinates. Okay, spherical coordinates is not included in the midterm. Sounds good? Okay, you guys enjoy the rest of your day. I will see you next on Tuesday morning.
Thank
See you, Professor. Thank you very much.